This is the Optim Update. I'm Bogdan Kristei, and today's guest is Arjun Subramaniam, founder and CEO of Factory Intelligence, a physical AI company training tactile foundation models for the real world. Arjun has personally toured more than 70 factories deploying robots, and his co-founder Mike Strope spent 15 years in packaging, including a president seat at a global packaging machinery manufacturer. We walk through his first deployment in electrical prefab, and we sit in the integration trap question that every robots as a service company eventually has to answer. Without further ado, here's my conversation with Arjun. Arjun, welcome in, man. How are you today?
Hey Bogdan, nice to meet you.
Are you ready to talk about intelligence in factories or what?
Yes, I am very excited, and you know how I am. I can speak for ages on this topic, so let's get started.
I will cap you at some point, but for now, for now, walk us back to where this all started, right? So you came out of Purdue,
Mhm.
kind of industry 4.0 research. You then spent some years deploying robots inside actual real factories. I think you said 70 factories or something like that. And Mike has also spent a number of years, I think 15 years in packaging. So
Mhm.
what did all of that teach you guys that pulled you toward factory intelligence as a company?
Mhm. So yeah, like you said, I've got a weird, broad history. I spent a lot of time doing research on robots in Purdue,
Hmm.
but then I've also done about 70 factory visits across America, specifically in the Midwest. And my co-founder Mike, he has 15 years of experience doing industrial automation. So not only touring factories here in America, but across the world. I think the biggest kind of takeaway from this is when you're doing robotics in a lab, it's hard, but it's way easier than you'd think.
Hmm.
Because the further away your robot gets away, I mean, the further away your robot gets from where you are, the
Hmm.
complexity, um, the complexity grows exponentially.
Got it.
Because, when you're in a lab, you're able to be in a very tight loop. If
When
something
you say
breaks,
lab, do you mean academic lab? Is that what you mean?
yeah, I mean
Okay.
academic lab, research
Got it.
lab, where
Got it.
most people who are working on this exact field come from. I mean, I'm from the same too, but when you're in a lab, you're more on constraint to like resources, you don't have as much robots, as much
Yep.
compute.
Yep.
But when things break, you're able to quickly iterate on it. It doesn't have to look pretty
Hmm.
after it's
Hmm.
fixed. It just has to work enough to publish a paper. And publishing papers is nice. It allows you to make breakthrough research. It allows you to demonstrate things as a proof of concept. But there is no like requirement of reliability in a paper. There's no SLA attached to. There's no service level agreement. There aren't no customers. There aren't people that get mad when it doesn't really work
Hmm.
reliably.
Hmm.
You just need to be able to replicate it. You just need to be able to reproduce it for it to be viable research. But in factories, you need to be able to reproduce it day in, day out, every single second, because if you don't, some of these production lines are $20,000 an hour. Every minute can cost you greatly. Especially when you go to like food manufacturing, produce, these lines go by extraordinarily
Hmm.
fast.
Hmm.
Dairy lines, ice cream, these products are going by extremely fast, and every minute of delay cascades down the line where you have milk expiring because
Yeah.
your robot screwed up. So that's the one thing that you don't really see in labs. There's a
Yeah.
huge gap between demonstration and deployment. So that's where the years of experience that I have in actually deploying robots in actual factories serves me greatly, because you have to make sure it works as a demonstration, but it also has to work every single day for your customer, and you're far away. Once you
Yeah.
deploy, you can't really sit there and babysit it every time. You can't watch it like a hawk. You can't cherry pick the times it works versus it doesn't work. It needs to work when you're not watching. It's like a tree that falls in a forest.
Yeah.
It just needs to keep
Yeah.
chugging away. So probably the biggest thing.
And your COO is actually a packaging machinery veteran, right? So maybe
Mm-hmm.
that speaks to the same.
Yeah, absolutely. So when you think about what I did, it's more systems integration. It's going project to project, figuring out a customer's pain point and putting together the things. But what he has a lot of experience is in productization. How
Mm,
can you make a single product that does automation in factories, but is reproducible across factories in 60 countries? And his company, his previous life, they don't work directly with the customer too, in most cases. Say they not only work directly with the customer, a
mm,
majority of their business comes from distributors. So they
mm,
have over 175 distributors. So in a lot of cases, you're not even having direct contact with your end customer. You need to build a product that's so intuitive, works so well that you can pass it off to someone who can then implement it. And, their reputation is on the too. Your distributors will no longer carry your product if you can't properly support it, if it doesn't work, if it doesn't integrate well. So he has a lot of experience building machines that can be deployed easily with very low marginal cost in
yeah,
factories. So when you
got it.
put this experience together, you're able to truly deeply understand a customer's problem and then find a large enough market and then build a reproducible system and
Mm,
then not only deploy directly with our customer but build it in a way where we can scale it up through various channels. However, I am a huge proponent of being fully vertically integrated, doing as much of it as possible by yourself because
mm,
you have so much more control over the entire stack. That's why even when it comes to robotics, we try to be as full stack as possible. We don't even buy our teleoperation frameworks. We actually build it ourselves from the scratch. So anytime we need to remote in from India to solve an issue, it's our own software from end to end that we're using. So this allows us to benefit from the entire stack of robotics.
So just a couple of things to get you going here. So you're a one-liner for the company. I know that changes all the time.
Mm-hmm.
Would love to hear that what it is now, especially how it relates to your strategy, which you call useful now, right?
Mm-hmm.
And as you talk about that, I would also love to understand where do you think the dominant robotics narrative is mostly wrong
Mm-hmm.
right now, right? So can you walk me through that?
Yeah, so our one liner is we're building autonomous robots to do skilled labor. These are tasks that take years to learn, but minutes, if not hours, to get tired of, and seconds to get hurt doing. So
Mm,
these are tasks like stuff that electricians do, construction workers, maintenance technicians, the people who have the knowledge to run CNC machines, mills, these types of machines that produce the stuff that we use every single day. This is called tribal knowledge. Some people
mm,
call it, this is called tribal knowledge and enterprise knowledge. This is stuff that people are retiring but aren't training enough people. No one wants to do an apprenticeship anymore. No one wants to go work in a factory.
yeah.
Everyone wants a cushy desk job or they want to be an influencer, but no one really wants to pick up heavy things and place it or screw things in hunched over a table all day. So we are really building robots that can do these tasks. We are putting together the best of the physical AI models, or we're putting together best of physical AI models for their power and their flexibility, combining that with the traditional classical robotics for its reliability and safety. We build purpose-built hardware on top of off-the-shelf arms and the software that actually ties it into our customers' systems. So it's a fully integrated part of their business, like a worker that they've had for 10 years. What we believe that is a few things that the industry kind of gets wrong is one, you can't buy your way into a large enough data set or a deployment. You have to have paying customers, and your stuff or your hardware, your robots need to be doing real work. This is kind of like the Tesla and Waymo
Mm,
self-driving kind of dilemma, Waymo was under Google, so they had billions and billions in advertising money to burn towards this.
mm,
Whereas Tesla sent actual cars doing real work, useful work for people into the world. People thought self-driving was solved for the longest time,
mm.
but the long tail just ended up getting longer and longer and longer. People said self-driving was solved for the last 10 years, but that hasn't been the case. And with robotics, specifically manipulation, that long tail is even longer. Because when you're in a car, the only contact you have is with the road,
Yeah.
You hope to not touch anything else. But in robotics, you're constantly touching things, you're constantly pushing on things, you're exerting forces on things, things are exerting forces back on you. So the long tail is extraordinarily long. There's such a high dimensionality of things that can happen, not only in a home, not only in a park, but specifically in a factory where there's such a high density of different, like high dexterity, contact rich tasks. So we believe that there's not enough money that can be raised that gets you to the point of bootstrapping large enough data sets of actual manipulation doing real world tasks, that you have to start with the long tail first, build specialist systems that are doing real world work, and then you can generalize enough to then build a foundation model for industrial work. And another thing that we also believe is that vision is insufficient to do these tasks. People have over-indexed on vision alone because it's been easy to scale. I'm not someone who, hasn't learned the bitter lesson. I believe that scaling is the only way that you can truly achieve, the generalized robot models that we need. But you can't it's been easy to scale vision alone. It's been easy to do kind of cherry pick demos. Vision gets you kind of to the middle of the bell curve where you can choose a lot of lab tasks. You can pull a lot of data from the internet and you can scale based on that. But when you want to do real world tasks where your robot is actually interacting with things that don't change visually, that's where vision fails. In other ways, like vision, current models right now are relatively stateless and vision based. So there are a few companies that are working on enhancing the memory for models, like, Rhoda has demonstrated some memory capabilities, Generalist as well. Pi has demonstrated their own version of memory for VLAs. But currently, most models are relatively stateless. They've got a very short memory, and whatever they're doing in their environment has to change visually for the model to understand that this part of the subtask is done and I need to go to the next. But for a lot of industrial tasks, that just isn't there. These things aren't deformable in ways. So, like, if you're picking up a bag of chips, you know how much pressure you're putting on it based on how much the bag is deforming. But when you're picking up like a block of metal, how do you know? When you're inserting a block of metal, how do you know? A lot of these tasks, there isn't a visual differentiator between states. So you need other modalities. You need force feedback. You need torque. You need tactile sensing. You need other modalities for the robot to understand, these contact-rich tasks. Insertion, assembly, screwing, welding, bending, these types of really contact-rich tasks that people can do with their eyes closed. Vision-only models just can't do or are extremely slow at doing. If you've seen the new demos from Aka Robotics, the way they're able to move so fast is because tactile features are just so much lower dimension. You have so much less data, but the data is more high signal. That's why when you're trying to grab a kind of pen out of a bin of pens, you think, oh, grab the pen, and then you can just quickly move till you feel a single pen and you can grab it out. But a vision-only model has to process, super high dimensional, tons of features at every time step to see, oh, is the pen in between my grasp? Have I grabbed it yet? And then when it picks up, is the pen still in my grasp? Oh no, it's fallen down. I need to do that. And when there are boxes going down at like 5 boxes per minute on a production line, like this is way too slow. You need to be able to combine other modalities where you can plan at a high level with vision, but a lot of this feedback can be given through other tactile modalities by moving really, really fast. So that's why we believe that vision alone isn't enough. But you're not going to be able to bootstrap a large enough tactile data set by teleoperating robots or by deploying enough data collection devices to do that. But again, we're very, we're very AGI pilled on everything. We believe that robotics is the way, and we believe in various data sources, egocentric data, just pure video data, UMI style data collection devices like what Sunday is doing and what Generalist is doing. We believe in all these modalities, but we believe to truly scale this up and to have a tight feedback loop between your research and your deployments, you need to have a fleet of robots. Tesla is able to push so many software updates so frequently because they are able to, one, test their experiments on a large enough sample size But once they make the progress, they're able to deploy it and get feedback very, very quick on a large enough sample size. So
Interesting.
this kind of loop helps them iterate very, very fast, and they benefit from scale for this reason. So robotics right now is extremely early. It's an extremely diverse field where people are betting really big on various theses. Some people are scaling VLAs, old models. Some people are going heavily on egocentric data. Some people are going very heavy on reinforcement learning. Some people data collection devices. So there's so many improvements across so many different tracks that they're all kind of merging towards one thesis. There isn't one kind of scale is the only way, like in LLMs. There are so many different fields, and to truly benefit from the breakthroughs from each of these different tracks, you need to be a full stack robotics company that's building your models, that's building the hardware, it's building the infrastructure and the software, and have actual customers to benefit from the improvements of models. This is, in a long way, this is kind of like the same bet people are making with agents right now.
Mm.
People are betting on different thesis, and I'm going to make a better model. But as one model gets better, the value of your company or what you're working on decreases. People are now blasting on Twitter or X, every single day. They're like, build a startup where your market gets bigger as the agents get better or the base models get better. That's truly what we're working on too. As the foundation models get better, as the backbones get better, as the infrastructure gets better, our business only gets bigger. We're able to tackle bigger tasks, longer horizon tasks, more dexterous tasks, more complex tasks, more dangerous tasks. So we are uniquely positioned as a full stack robotics company working on useful now tasks to benefit from the entire kind of wave of improvements across the industry.
So that's a claim that you have, that you're the only company occupying the application specific full stack quadrant. So that's a super strong claim. And my question would be, why hasn't anyone else built here?
It's for that reason, because there isn't enough infrastructure to be full stack. When I say only, I'd say only in our field. There are a very few, you can count on both hands the number of vertical companies that are working on real world customer tasks. Everybody right now is trying to mirror what's happening in the software space. They're building models, they're building infrastructure, but no one's putting it all together for real customer tasks.
So the model first players would argue that you lose because their generalized capability arrives before you finish your vertical by vertical build out. So what do you think is the best version of their argument, and then how do you push back on that?
So the best version of their argument is that generalization helps build the model. The more data you have, the more diverse data you have, the more different deployments that your robot can do, it all feeds to this God brain. What people haven't done is actually deploy these models in real world use cases. Getting a general labor is only table stakes. People can hire a 19-year-old kid who hasn't gone to college off the street just as easily as they could get their robot. They're not really looking for that. They're looking for reliable labor that understands their business, that understands the full end-to-end of their business, how to not only be good as a human, but superhuman, be reliable, work 24/7. So yes, they can get generalist models, that's fine, but that's like getting a temp off the street. What we're selling is a specialist, someone who's spent 10 years in your business and understands your business end to end. And for this, the large model players just cannot go to all these different industries and fully understand their capacity end to end. There's a diffusion problem. It's the same question of, will Claude be good enough to take out your agentic startup? But if you can go end to end, truly understand your customer and build something around their business that harnesses the power of these models, then you're the true winner. The applications layer truly wins, not the model layer, because that's where the value is generated. And that's where we sit too. As their generalist models get better, our specialist applications get even more verticalized, even more specialized, generate even more value.
Yeah, so the platform providers would maybe argue that you're just selling expensive work cells, right? So then how do you push back on that argument?
So that's the problem with the platform providers too. They have to be general enough to solve the problem for all their different customers. What we can do is work with multiple different platform providers, multiple different hardware providers, and build the solution that delivers the best labor output for our customers. It doesn't really matter, what your hardware does if it doesn't do the right thing for your business. So we're able to, help our customers avoid lock-in too with these different platform providers,
Yeah.
that we can build kind of the right hardware with the right solution and allow them to be flexible in the future
Yeah. Yeah.
with our
So
robotics as a service model.
yeah, interesting. So one thing I wanted to ask you about, I think that most of the well-funded robotics bets, like humanoids, general purpose foundation models, they're still, in my opinion, years from production deployment, right? So that's clear to a lot of us. And I'm wondering if what you're saying is true, that if useful now works, I'm wondering what's your thought on what happens to the humanoid
Mm-hmm.
timeline, right? So how does that bet in humanoid turn out to be maybe 5 years from now if this useful now kind of works?
Mm-hmm. I think there's a weird like analogy I like to give is like when
Mm,
you're trying to climb a really tall tree, there's no point climbing other shorter trees nearby it. So if you want to actually deploy robots, you need to work on deploying robots because there's a huge set of problems reliably deploying robots at scale. Companies are making that long-term bet of, can I make something general enough to make it easy to deploy? But when they get to the point that they're actually deploying, that's when they open the Pandora's box of deployment related problems. What we're building right now is that go-to-market motion, that deployment motion about truly understanding what it takes to have robots working at scale right now.
yeah.
So when they do get to this bet 5 years down the line, they are going to be leagues behind what we're working on right now. But what that changes for them too is that doesn't really shrink the TAM in what they can achieve. It just expands the opportunities in which they tackle. There are far more general tasks that can be taken, the exploration of the seas, building data centers in space. There are so many tasks to be handled that our tasks that right now generate really high value will
Mm,
be captured by the
got it.
specialist robots that can produce things in the best possible way. You don't need a thing with two arms, two legs, and a head to produce wall outlets or to
Yeah,
build
so
buildings,
that's great. Let's talk about maybe a specific example. So your beachhead is
Mm-hmm.
electrical
Mm-hmm.
prefabrication, right?
Mm-hmm.
So most of our listeners never been inside a prefab shop. So maybe you can paint a picture for us. What's actually happening in there?
Mm-hmm.
What's in the day of the life of a prefab worker? And
Mm-hmm.
then why prefab and not live construction sites, right? Just walk us through that entire thinking, please.
Mhm. No, that's a very, very good question. So, before, what people used to do is you'd have these union electricians that have 20, 30 years of experience. They bring all the raw materials on site when they're building a house and they start assembling things, putting it together. Like if you want an outlet that goes on your wall, the stuff that you plug your phone charger into an appliance into,
Mm,
first they take an outlet that might come from China, then they take wires, they bend a live wire, a neutral wire, and a ground wire. They hook them onto the outlet, screw them in,
mm.
tape it, and then take a conduit wire that goes from the outlet to the junction box, cut it to length, and then install it into your wall. So imagine doing that 100 times for a house or 10,000 times for a building. This is the reason why buildings used to take so long to produce and are so expensive to produce. People have been working on making this cheaper and cheaper. And one big change to how construction is done that's significantly reduced the cost is this concept of prefabrication. It's how much of the material and how much of the building can you build offsite in a centralized location with machinery and labor, and then how, can you bring it on site with kits and quickly assemble these buildings. That's how, buildings that used to take 2 years to come now get put together like Legos in a few months. That's how you can see a skyscraper being built in a year or something.
So maybe
So,
a good next kind of follow up here would be, why building outlets first, right? Of all the
mhm,
tasks in a prefab shop, what
mhm.
made that the right starting point? And maybe here you can talk a little bit about the like a prefab cell E1. Like what's inside
Hmm.
that work cell? What's it doing? What's the
Yeah.
operator role? Yeah, could you walk us through that?
Yeah, so right now our robots are deployed with our first customer, Houston Electric in Indiana, building these outlets for their electricians that go on site. Right now, the prefab cell E1 is our first pilot production cell that has 8 robots in it that can produce outlets for $3 per hour, which is 10 times cheaper than equivalent labor, and can produce 3 times as many plugs. So it's essentially 9 times as productive as
What's
an equivalent.
what's an outlet? Like what's included? Just walk us through it. Is it
Mhm.
just the three wires that you connect to it, or why does that need to be
So
manual? Kind of walk us through.
the robot bends 3 wires. Electricians usually use pliers, but we've given the robot a tool like a jig to do it. So it bends 3 wires, puts a hook on it, then picks up the outlet, tails the outlet is what the electricians call it, but it's really just hooking that wire onto the screw that's been pulled out, and then it takes a screwdriver and then drives that screw in so the wire is secured onto it. So then you have to put 3 of these wires: a live wire, a ground wire, and a neutral wire, and this is what's wired up to your house. That's why you see 3 holes or 3 prongs in your plugs and 3 holes in the outlet. So one's a ground, one's a neutral, and one's a live, and that's how you get power from the grid. So this gets tailed on, screwed, and then an electrician checks it and then tapes it. So right now the cell, what it's doing is it's prefabricating these outlets, because for every house, whoever the engineer is, whoever designs the house, chooses which outlet, what specification, what wire to use, and then sets it. And then the electrical contractor has to order all this stuff 6 months before the project gets done, and then build maybe 10,000 of these. So the moment they get an order, they press start on our cell. It pulls all the information from their ERP system, so it knows what plugs to use, what wires to use, what specification to build this to, and it builds the exact number of plugs they need to schedule, so they have it ready to go. It's basically from order to stuff shipped out in your truck. It's kind of like a building that produces buildings before you go and put it on site. So we've started with electrical outlets right now because that's one of the most, contact rich. It's one of the most boring, repetitive tasks that every single prefab shop has to do. Every single building in America has to have an outlet every 8 feet. This is something that we need to
Interesting.
fact check before you put it in, but I'm pretty sure it's every 8 feet you need to have an outlet, and in specific other scenarios you need like more outlets. So these things are in every single building, every single data center. Like, the reason why we cannot produce buildings fast enough is because we don't have enough labor to produce this. That's why in China you can build, miles of highway per day, but in America it takes so long, is because of the labor and the permitting and all this regulatory stuff. Maybe that's a bad point. The reason why you can build buildings so cheaply in India and China and all these developing countries is because you have an abundance of labor there. So you have all the raw material, but in America we have such a shortage of people, the skilled labor or tradespeople, the people that plumbers, electricians, construction people. So if we can truly build robots that can do their job, or at least assist their job, then we are unconstrained in the number of houses we can build, buildings we can build. It just becomes cheaper, faster.
Yep.
Like, if there's a data center that's coming up in a state, all the electricians are booked out for years in advance. People are flying electricians out from countries. This is
Yep.
more like labor on demand. These are skills that we can never lose now because we have robots that can do the task.
Okay, no, that's interesting. Let's talk a little bit about the technology. So we
Mhm.
were chatting before this call that a month after you kicked off your project, you had this wire bending model that
Mhm.
was generalizing to collars you hadn't seen
Mhm.
before, so it hadn't been trained on. So
Mhm.
curious, like what was happening inside the model when that started working?
So we noticed that because we're adding all these additional modalities in, we're able to get so much more performance from way less data. This is less than 5 hours of data on site across all our different tasks. We're able to build that plug. This is because there's a grounding between what the robot sees and what the robot feels. So it's able to do these tasks with way less data because there are fewer states that it can be in when you have this tactile data as well. So that's why we're able to see such fast improvement in our models. And that's why we believe that every single new task will be faster and easier to deploy as the robot sees more materials, as it feels more materials, as it handles more materials. All this transfers and generalizes. And we get it for free. If not, we're getting paid to get all this data because our robots are deployed doing real world labor.
Okay, so every robotics as a service company eventually runs into the same wall. Each customer needs custom fixtures, custom work holding, custom safety setups, custom support in general, right? So the fully loaded development cost ends up wrecking the margin. So I'm curious, like, why doesn't that happen to you, and how do you think about that?
Exactly. And that's the one reason why we're not focused on robots to automate manufacturing and logistics. Rather, we are building skilled labor. These are the people that are trained and given the tools to do a very specific task across different sites, across different jobs, across different buildings. We are building the electricians, the machine tenders, the maintenance technicians of the world that truly understand the job they're doing. They don't really care where they're doing it, who they're doing it with. So when you get into the kind of the nuts and bolts of automating a specific task, this might be, this might change between customer to customer. But when you look at the people that are doing the task, that is relatively common between customers. And that's where our platform really helps us quickly make the modifications necessary to integrate well into our customer too. And that's why having a good software platform that you're not treating every deployment like a lab demo where you're prompting the robot to do what it needs to do or trying to make it look good for a video. It needs to be well integrated into their ERP system too. So that's where your software has to be modular enough where it understands all the common different software, the data sources like data historians in factories, the common ERP systems like whether you have Oracle NetSuite or you have SAP or one of these common ERP systems, we need to be able to interface easily with this. So having a modular platform helps us avoid a lot of these issues, but focusing on very specialized tasks helps avoid and mitigate a lot of these concerns. It's the reason why you can hire one person that worked in a different factory into your factory and still retain a lot of the skills they still had because their job might be, what they're working on might be different, but what they're doing is very similar.
Interesting. And then at what scale do you actually know whether the deployment economics work? When do you think you'll have that answer?
And that's not an issue if we grow profitably, but the scale that we're looking for right now is replacing or at least having one robot to one skill, like one robot to one electrician in America over the next 4 years. So we want to have just as many robots doing these jobs as humans doing these jobs, because then we can get a large enough sample size, which lets us know if we're just as effective, if we can be better than humans.
So if you get a question like, when does your data flywheel, when does that become cheaper for deployment, help you become cheaper for deployment n+1 versus then n? How do you kind of answer that question if you ever get it? What does that data flywheel need to even look like for that to be a possibility?
Right now, for our data flywheel, we're looking for 50% success rate on any task we try to achieve right now. It's not about scale of robots, but it's really about scale of data success. Because if we have more than a 50% success rate, then we can just improve exponentially. It's really about getting more than 50% success rate across a large enough scale of robots. Then we can collect the higher quality rollouts versus lower quality rollouts and build that self-improving data flywheel. Because if we're less than 50%, then we're not improving at a fast enough rate for us to hit that critical mass. But if we're over 50% success rate and we have more like each index, I'd say, like if we're working on 5 tasks, we want 5 robots. If we have 50 different tasks, we want 50 different robots. I guess that's the way I'd answer it.
Okay. So I see more and more that the touch modality is becoming more talked about. Until recently, I felt like that was a little bit underweighted.
Mm-hmm.
So how do you view this concept, like touch becoming more important?
I think Touch was a great proof of concept. It was great to bootstrap from, let's say, -1 to 0 or 0 to 1. It got us a lot of the way because we were able to benefit from all the internet scale data, all the data on YouTube, all the images, VLMs. And that's why we were able to improve so fast with vision. But I think people are realizing that vision is saturated. We've gone a lot of the distance we can with vision. And for all the reasons I mentioned prior, vision is just, you're throwing way too much compute, way too much information at tasks that you don't need to do. So that's why I think people are now realizing that you can make a lot of headway when you incorporate tactile data as well. One, you're able to do tasks at real time speed with compliance, which is one thing that has been missing from a lot of stuff that you've seen in robot learning, where everything is at least like 8 times, 6 times to 8 times, and people are using hockey sticks near the robot because it's not safe for a human to be around. But now you're seeing stuff happen at 1 times, if not half times speed around humans, because you're able to use tactile data, and now you're able to benefit from the visual features, the high level planning you get from vision, but also the low level features and the very fast high frequency data you get from touch sensing. So one, I think touch sensing is now like, necessity is the mother of invention. People have been struggling with slow models that can't do very fine manipulation. So now I think touch sensing is coming in to fill that gap of fast action with very fine-grained manipulation.
Yeah, yeah. So most robotic teams either bet purely on end-to-end neural nets or pure classical control. You're combining both. I wonder why you think that's the right design. And if you can walk us through your architecture, that would be super interesting to hear about as well.
Yeah, what we get by combining the best of what we'd say like neuroclassical controls is we get the flexibility of neural networks, where it works really good in the middle of the bell curve, where there's some variability, but it's inside the distribution of the network. Versus classical controls lets us deal with the long tail scenarios, the stuff that's very hard to bring in the distribution of the model. One, we're able to help the robot fail more gracefully and recover from these different scenarios using classical controls, but we're also giving kind of what I'd call like safety boundaries to the robot, or affordances, where we have no-go zones, or we have collision checking for the trajectories that are planned by the robot to make sure it's actually viable. If not, how can we edit these trajectories to make it actually viable, given 3D representations of what it sees and other classical robot motion planning methods. So we're able to use trajectories generated by neural networks, but edit them and check them and generate various trajectories and sample based on classical methods by using traditional motion planning to make sure that these are actually viable trajectories. And we can also simulate out to see the forces that these trajectories exert on certain objects that are in the task space if we want to hit. So we have sort of compliant control where the model's not only outputting the trajectories where it trajectories it wants to hit, but also the various forces it wants to hit during that. So if you see when you're trying to pick something up, you want to close your hand, but you're closing your hand till you feel something. So that's a sort of closed loop compliant control. And we're doing the same thing with our robots, where there's a higher level position-based planner, but there's a lower level compliance-based planner that can execute these trajectories with the right amount of force and until it hits a desired state. So this is what we mean by combining the best of neural networks and classical controls. It's both for safety, reliability, but also performance.
So you have a world action model that takes image, proprioception, tactile, action, future states, all of that as inputs, right? Does that ever get to be too complicated? What does that give you that maybe simpler architectures don't?
That's actually a really good question, and it's got a weird answer. That actually gives us the most simple way to test our thesis. If you've seen the architecture, it's very similar to what NVIDIA published with Cosmos Policy, where they're able to change just the latent space if a video generation model, not the architecture itself, to produce robot actions. We are able to modify this or extend this for tactile sensing both on the input side and on the output side to test our thesis and to test and build the infrastructure necessary to actually incorporate these various modalities into robots without having to, um, without getting stuck in the random quagmires of architectural changes that lead to training instability. So we didn't have to waste a lot of compute and time wrangling the model. We were able to just add the modalities we want to add. Of course, this is way slower than we do need because it's a larger model with a lot of additional, additional little things in it that make it slower for it to do inference. But we want to then take our learnings from this initial model and then move to more optimized methods. Something similar to what Dream Zero does with a causal world model and an IDM. Dream Zero does not use an IDM, but we also believe that that's just way better for stable training. So more with a causal world model, not as large of a model as Dream Zero, but again, extended with tactile sensing from all the learning. So it's really it's more a decision to be economical and fast. I was using this model.
Cool, man. I mean, this is a fascinating conversation. We could go forever. I think it's going to be super helpful for folks to just hear your thinking on this. Maybe just 2 or 3 questions to kind of round it up a bit towards the end here. First one, what do you believe about the future of robotics that most people in the industry still disagree with?
The contrarian view would probably be that you can buy your way to a large enough data set necessary to train models that are not only vision based. I mean, there are so many different modalities that you need for a robot to be actually human or AGI, artificial, physical, general intelligence, whatever. You still need to be able to touch things, you need to be able to hear things, you need to be able to smell things. And these are all data modalities that you can't get from the internet alone. So you're going to end up spending a lot of money trying to get this out from the real world. So you need to find that data flywheel, which actually gets you to large enough data sets without having to spend millions and billions in venture money.
Yeah. All right. So if your company, Factory Intelligence, works, what does the world look like in 5 years?
It looks like data centers on the moon, mining asteroids. It means that we're truly uncapped with our production capacity. People draw parallels to China all the time, but that's really not that's a very low hurdle. That's a very low bar to set because we can do so much more once we solve the problem of 24 hours in a day that humans have. We're limited to 24 hours per day per human. Once we can uncap that, that's when we have true abundance and the ability to take on these moonshot projects with very low marginal costs. That's why I think that there'll be data centers on the moon and, mining asteroids once we can solve the base problem of skilled manipulation.
Yeah, all right. Where can people find more about you and what you're building?
So you can go to factoryintelligence.com. We are updating the site daily to give you guys more information on what we're working on. You can email me at arjun@factoryintelligence.com. We're always looking for top researchers, amazing customers to help us build the future of robots, and also investors that understand what it's like to deploy hardware and what the future could be like when we succeed.
Awesome. Well, this has been great, man. Thank you so much for your time, Arjun.
Thank you for having me, Bogdan. It's always a pleasure to chat.